This video is for Math 116, and this is for section 3.2 on arithmetic and geometric sequences. And it's pretty straightforward. The arithmetic sequences have a constant difference. And the geometric sequences have a constant multiplier or constant ratio. So for example, well, let's use the one example from the textbook. 2, 6, 18, 54, 162, and so on. So the constant multiplier is if you recognize, oh, 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54. So there's your constant multiplier to get the next term. If you're thinking of like a recursive definition. The constant ratio is if you take each term and divide it by the previous term, you get the constant multiplier or constant ratio, depending on how you want to look at it. So that's the basic fundamental idea about arithmetic and geometric sequences. So let's take a look at the problems on page 111. So problem 2. We've got 9, 19, 199, 1999, and so on. Now notice that we don't have a formula for this, and I suppose we could build one, but it seems pretty clear what the pattern is, right, is to, well, just to add a 9 on the back, okay? Although it starts out, let me take a look at that. Yeah, that going from the 9 to the 19 is not as clear what's happening. When you go from here to here and here to here, you're just adding a 9 onto the back. But this one is a little bit different. But in any event, there's no constant difference. There's no constant ratio. And so this is neither arithmetic nor geometric. Okay. Let's see here. Problem 4. We've got 15, 7, negative 1, negative 9, negative 17. So if you recognize 15 minus 8 is 7, 7 minus 8 is negative 1, negative 1 minus 8 is negative 9. So this has a constant difference of negative 8, or 8 depending on how you want to look at it. So it is an arithmetic sequence. Alright, let's see here. Oh, and the constant difference there is negative 8. And that makes a difference to have that negative in there because that indicates that it's decreasing rather than adding 8 every time. Problem 6, 100, negative 50, 25, negative 12 and a half. So we don't have a constant difference. For one thing, it's alternating back and forth. And even if you look at the absolute values, you still wouldn't get a constant difference. But you do get a constant ratio where there's a constant multiplier of negative 1/2 here. Okay, so this is a geometric sequence, and it has a constant ratio of negative 1/2. Problem 8. Let's see here. 1, 4, 9. So this one, again, you can see there's no constant difference. The difference here is 3, 5, 7, 9. There is a pattern in the differences, but it's not constant. Okay, same thing with the ratio. There's no constant multiplier here, and so this is neither. although this is a good sequence to be able to recognize because it's n squared. Okay, being able to recognize those perfect squares comes in handy when you're analyzing these things. Okay, problem 10, 12, 15, 18, 21, 24. And so that one looks like a times table, and we've got a constant difference of 3. And so this is an arithmetic sequence with our d equal to 3. Problem 12, 5, 15, 45, 135, 405. And here you can see there's no constant difference, but we do have a constant multiplier, right? We're multiplying by 3 every time, and if you do it by dividing, you'll get an answer of 3 as well. So this is a geometric sequence, and our constant ratio is equal to 3. Let's see here. Problem 14, 2, 4, 6, 8, 10. And so here you do have a constant difference equal to 2. And so this is an arithmetic sequence. And in problem 16, I believe this is the Fibonacci sequence. 3, 5, 13, 21, and so on. So this one, you can see there's no constant difference, there's no constant ratio, and so that one would be neither. But again, this is another one I think that it's good to be familiar with. This is called the Fibonacci sequence, and it's defined recursively. You say A1 is 1, A2 is also 1, and each term will be the sum of the previous 2 terms. So that's how you get the 2, and then 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, and so on. It's very challenging to come up with a general term for this sequence. If you poke around on the internet a little bit, you may find some formulas for them, but they are not simple by any means. So that's it for section 3.2. This is a pretty simple and brief section. And really all it is, like I said, is identifying arithmetic and geometric sequences and then finding their constant difference or constant ratio. And that's pretty much it. As always, if you have any questions, please let me know. And we'll keep moving through chapter 3. Thanks.